Hi, everybody. Let's take a look, or a beginning look, I should say, at our atmosphere. And the first thing you think about atmosphere, it's what we walk in and out of our house every day outside, or our apartment, or our caravan, or our old schoolhouse, if in my case, in the fall. And temperature is a really big indicator of things that change in our atmosphere. We're coming into this season where we have little white flakes coming out of the sky. And we're leaving the season where we're as likely to see that in water form. A quick review on temperature. We've already done this once this year, so this should be easy and quick review. So remember, things in science come round and round again. So the United States was one little country in Africa, and I forgot there was one in the Middle East too. Still uses the U.S. standard or the imperial system, the inches, miles, yard, foot, acre system. Everyone else in the world uses metric. And we can go through Celsius, Kelvin, Fahrenheit. A quick review. Remember, Kelvin is the one used by scientists because we go to the point where absolute zero is everything stopped moving. The protons, the neutrons, electrons, they all start vibrating. And that's just Celsius shifted down by 273 degrees, which is the point of absolute zero in Celsius. We don't talk about Fahrenheit very much in science because, let's face it, 100 minus 0 is a lot easier to figure out than 212 minus 32. That's not a number you keep in your head that often. So Celsius, remember, Kelvin took Celsius and shifted it down 273 degrees. So there are no negative numbers in Kelvin, which is a nice thing. To put this into perspective, air freezing, like air around you freezing and dropping. The gases are solid. They are no longer in gas form. In Fahrenheit, that's negative 320. In Celsius, it's a negative 196. And in Kelvin, it's 77. Remember, no negative numbers in Kelvin. Now, we can go for the freezing point of water and the boiling point of water. We've gone through that enough. Just to put this into context, your body temperature in Fahrenheit, 98.6, 99 degrees, let's say, is 37 in Celsius and 310 in Kelvin. Not really worried about Kelvin. So let's just look at these two. Room temperature, if we said if you like it on the cool side, you want 68 degrees, that's about 20 degrees C. So if you're hearing a temperature 20, 21, 22 degrees, you're probably talking a comfort level that humans like. This was a cartoon from when I was little. And let's see if I can make that go away just a little bit. All right, this is Peanuts. It's Charlie Brown and Snoopy. Think metric. Wow. There are 10 millimeters in 1 centimeter, and 100 centimeters in 1 meter, and 1,000 meters in 1 kilometer. I can't remember all that. What are they trying to do to us? I just got inches and feet figured out, Marcy. Now they're throwing metrics at us. I'll go crazy. You'll catch on before you know it, sir. Somebody's always trying to change things. If those people, it's the people on the school board, they're always getting carried away. Give them a millimeter and they'll take a kilometer. See? You're catching on, sir. And this was kind of appropriate when I was younger than you are, because for 2 years in my elementary, we were not allowed to use inch, mile, or foot, or acre, or any of those other words that go with the U.S. standard system. We were taught metric because there was a presidential order by then President Jimmy Carter that the United States would go metric to match the rest of the world so that trade would be easier. We wouldn't have to have conversions. And so when I was young, all the road signs had miles per hour, and then underneath it kilometers per hour. So people would start seeing what the equality was between the two systems. It's why you still to this day see bank temperatures with Celsius and Fahrenheit. It's a leftover from that. We aren't metric. You guys have learned inch, mile, foot, yard, acre, all of these things, because one of the platforms Ronald Reagan ran on was that we're the US and we don't need to be that. So he rescinded Jimmy Carter's presidential order by doing one of his own, and he got rid of the metric system. It's still used in manufacturing. It's still used in engineering. It's still used in science. It's just not usually used in everyday life. And for good or bad, it's what it is. It's also why we crashed a probe on Mars, because it thought it was in the atmosphere, and we did a conversion error here on the US side when the metric system came in from Europe, and they kind of forgot to convert from metric to US, and it thought it was in the air, but it had already crashed into the planet. It's very sad. So Let's just take a quick look at our atmosphere. I turned off the sound because it's really just music, but it's just showing you what it is. Above our Earth is this really thin layer of gas. If you had an Earth the size of a basketball, that thin blanket of gas would be about the thickness of a piece of paper. It's not very thick compared to the whole distance across the Earth, compared to our diameter. We call it our air. We live in something called the troposphere, the lowest layer of the atmosphere. We don't usually think about it, but it's where we live. Without it, let's see, what all wouldn't we be able to do? Well, breathe. There wouldn't be life. We need those oxygens and nitrogens and carbon dioxides and carbon monoxides and all those other gases mixing around. Without our atmosphere, we wouldn't have a blue sky. It would just be the black that is outer space. We wouldn't have clouds. So let's take a look and see where else they're going to go with this atmosphere thing. Aren't those beautiful? The clouds rolling in. That's in that lower troposphere. This is where we're going to have clouds, the bulk of them. Planes fly in the next layer up to try and avoid some of that turbulence that can be created by all that lovely air moving. It is one big swirling mass of gas, and that's really easy to see on this is what I want. And I'm going to pause it there because you can keep watching this on your own if you wish, but it just keeps it going on to show different layers of the atmosphere. But I think you're going to get the point in that we live in an amazing place, and without it, we're kind of, out of luck. That's why if you're out in the space shuttle that used to fly, or now the International Space Station, or SpaceX is about to launch some of our astronauts back up to the International Space Station, you can't go outside without a pressure suit. We need that atmospheric pressure. So let's take a look and see. I told you that we live in something called the troposphere. It's where our weather is, the tropical area, if you want to think of how to remember troposphere. We live in the troposphere. Above it is the stratosphere, and then the mesosphere, and then the thermosphere, and above it is the exosphere, sometimes broken into parts called the ionosphere. And we'll talk about that in a little bit. But these first four, troposphere, stratosphere, mesosphere, thermosphere, these four you're going to need to know. And if I gave you a picture like this, I would expect that you would know weather occurs in the troposphere. You aren't going to survive a parachute jump if you start up here. There's not enough. Think of it this way. Have you ever been to the bottom of a pool? There's so much more pressure on you because there's so much water above you. Well, not only is there water above you, but there's the whole atmosphere above you. Well, if we're at the bottom of the atmosphere, we have the whole layer all the way above us. And gravity pulls it down and it's packed nice and tight together. The farther up you go, the more it's spaced out. So you're not going to survive that. That's why airplanes who go just right at kind of that boundary of the troposphere and stratosphere have to carry oxygen just in case there's ever a depressurization to make sure you can breathe. So you'll notice there are these things in between here that's called the tropopause, the stratopause, the mesopause. And pauses occur with this change in temperature. Look down here. This is Celsius, because remember, we're science. We're starting like a little under 20, so it's a cooler day. Not, it's a nice fall day. Kind of think of our like 60-degree day. And from here, notice our temperature is dropping. And then all of a sudden, it changes directions and gets warmer again. And then it gets colder again. In fact, colder than it did on the last pause. And then much, much hotter. So every time this temperature reverses, that's the definition of where we're breaking one sphere into the next. So the troposphere at the tropopause becomes the stratosphere. Where it changes direction and temperature at the stratopause, now it's the mesosphere. And at the mesopause, it becomes the thermosphere. Exosphere and ionosphere is what we break those down into sometimes. So here's when we're looking at this. Think of it this way. Above us are all these different gases like ozone and things like that that protect us from radiation coming from the sun. That's why this temperature gets so hot, because all of that really energetic particles from the sun hit the upper layer of our atmosphere first and really, really heat up those gases. Now they're pretty far apart, so you could kind of like fly a space shuttle through and you're not going to hit that many hot ones, but they're there and they do. And then the farther down, so airplanes fly here. Supersonic planes are definitely up in the stratosphere. Radio sounding, we actually will send weather balloons up through here. You're going to see the space shuttle flying up, closer to the exosphere. Satellites are definitely up there too. There's these things, Everest. So to put it into perspective, Mount Everest is completely in the troposphere. Here's our ozone layer, and above it in the mesosphere, this is the layer that saves us from bombardment from space. This is where meteors get burned up. It's where we see our shooting stars. There's also something called lenticular clouds, which occur up in here, and usually they form at night. The northern lights, the polar lights, whichever you want to say, the aurora borealis or the aurora australis, they occur up in the thermosphere exosphere range. So our atmosphere is an amazing thing. Without it, we aren't here. We need that gas mixing around. We need it churning. It provides protection from ultraviolet rays. It keeps us warm. It keeps us hydrated. Think of the atmosphere as the blanket that keeps us warm. You'll notice that on really cloudless nights in the middle of winter, it gets super cold. Clouds actually act kind of like a blanket. The heat that's radiating up gets stopped by the clouds and isn't allowed to exit out into space. So it's usually warmer in the middle of winter on cloudy nights than on cloudless nights. It's that bubble of gas surrounding the Earth, and it's held in place by gravity, and that's important to know. Gravity is what keeps our atmosphere here. This is the same picture that we looked at before. It just isn't including all the cool things, like what flies where you see meteors burning up, all that. But this is a really nice rendition to show you. Here is the troposphere. It happens when the tropopause happens. We have a very distinct change in direction. Now we're entering the stratosphere. Stratopause, mesosphere gets colder, colder, colder. It pauses and changes direction into the thermosphere. These are the four that I would expect you to know on the test. These are the four that you're going to have to put in order. You need to know that it's troposphere, stratosphere, mesosphere, thermosphere. It's important to understand this is that layer where if you are in a little two-jumper seat, you're going to be flying mostly in the troposphere. If you're in a jetliner, you're just right at that stratopause, a little bit into the stratosphere. And if you're a fighter pilot, you're in the stratosphere. Meteors are burned up. Ozone layer protects us. Those are the good things that we know. So think about this. As altitude increases, the air becomes colder and less dense, which is kind of interesting because cold stuff usually shrinks together and gets more dense if we're all here at the same sea level. But in the troposphere, we get colder and there's not as much stuff packed above it, so it has more time, space to fill out into, and so it's less dense. When the temperature switches back and heats up, you're at a pause. In this case, we go from the troposphere to the tropopause and end up in the stratosphere. Convection currents happen because the sun's radiation does get through, and some of it, it heats up our car. We know that. And but it actually heats up everything. It heats up the rock. It heats up the water. It heats up you. As a matter of fact, you can feel warm on a nice sunny day. And what happens is that sun's radiation hits the ground. A lot of it's absorbed, but then it gets warmer than some of the air around it, and it radiates heat back out. And then hot air, as it rises, tends to cool. We'll do a whole worksheet on that. It's called adiabatic cooling. And as hot air rises, it starts to cool. And as it becomes more dense, that is colder, it will sink back down and you get convection currents going. And we have some really big convection currents, like at the equator. Think of that hot air at the equator rising, and think of the pole. It's really cold and sinking, and you think there's a big one, but because the Earth is spinning, it actually is broken into three. And those three are called Hadley cells. Those big convection currents actually determine where our deserts are in the world. They determine where the tropics are in the world. They determine which way our wind goes. We live in something called the prevailing westerlies. Our weather starts out in the Pacific Ocean beyond Seattle. Seattle gets it. My aunt lives in Seattle. And 2 days after what she gets, we tend to get it because it goes from west to east. But if you are my cousins in Florida, my aunt in Florida too, they live in something called the Northeast Trade Winds. And their stuff, you see it in hurricanes, actually starts in Africa and comes along the equator and hits the US. So we actually have converging areas of storms, and we'll talk more about that, but you need to know what's coming up. But those are all driven by these convection currents, by that uneven heating. This was one I drew 20 plus years ago. If this one makes you feel better, go ahead and use this one. Here's our ozone maximum, here's the stratosphere, the mesosphere, the thermosphere. We live in what again? Where is that weather? It's the troposphere. All right, let's talk about each of these layers a little more in depth. Basic characteristics. So in the troposphere, it gets colder the higher you go. It ranges in temperature from -50 to 20 degrees Celsius. Pressure decreases with height. That makes a big difference. Think at the bottom of the pool. There's more pressure at the bottom than when you're at the top, just because there's more water above you. Same thing in the atmosphere. The higher up you go, there's less atmosphere above you, so there's less pressure. It contains the bulk of our weather. It's where we live. And most of the gases in our atmosphere are actually found in the troposphere. And really important, it has liquid water. Without it, we'd be really thirsty. Stratosphere, it gets warmer. This is where those radio sounding balloons will go up. It's from -60 to 0 degrees C. Jet planes fly here. It's the home of the jet stream. And we'll talk more about the jet stream, but just know this, there are currents like rivers of gases flowing up there, and one of them is the jet stream. And we know that sometimes it moves over us and goes north, and sometimes it goes south, and that kind of determines if it's north of us, it allows that warm air from like the Gulf of Mexico to come in. But if it goes below south of Minnesota into Iowa, then it lets the cold air from the pole come down towards us. So that jet stream is a big deal in our weather making. So we'll spend a lot of time talking about that. The ozone layer, big deal in the stratosphere. It is oxygen combined to form ozone and it's struck by lightning. And so basically, instead of oxygen, which is usually 2 oxygen molecules stuck together, O2, that's actually what we talk about, oxygen that we breathe. It's actually called O2. Ozone is actually 3 together, and it can break apart a little more easily, but it protects us because of that. So it's about 30 kilometers above the Earth's surface. It absorbs most of the harmful ultraviolet radiation from the sun. Basically, think of it as Earth's sunscreen. Without it, we don't survive. We need its protection. The mesosphere has all of those fun meteorites burning up here. This is where the bulk of our atmosphere creates so much friction that those rocks hurtling through space, when they hit our atmosphere, are, like if you rub your hands together, they're going to get warm, right? Well, now imagine being a rock hurtling along at thousands of meters per second, or hundreds of meters per second, depending on the angle. They burn up. There's so much friction, they actually burn. And that's a good thing for us, because we don't want those things hitting our ground. We like them to be burned up, because you don't want to get struck by one of those. And they do occasionally, really, really large. And there's so many more cameras now, we can catch them in the act. And I'm going to search one. Here, I'll show you. Okay, I found this. We're not going to watch the whole thing, but this is, 15 years ago, 20 years ago, we would talk about the Tunguska meteor that exploded above, and it like flattened trees for a long way out. There's so many more cameras on police car dash cams, on buildings, that we actually start to see these, and they do happen periodically.
Hi everyone, welcome to the Earth Science Regency View podcast series created by Hamid.
That would be the wrong one. This is the one I want.
Anderson Cooper 360, weeknights at 8 and 10 on CNN.
The images look like something out of a movie. A tiny asteroid tearing through space at a speed of 33,000 miles per hour before streaking across southern Russia. Cameras caught sight of the white trail as it headed across the sky. And then this. An explosion of light, then a massive sonic boom. Strong enough to shatter windows and damage buildings. There were reports of more than 1,000 people injured, mostly from glass and debris. This video shows a children's judo class. Windows blew out here and in buildings around the region. Some people said they thought it might have been a plane crash. This is the aftermath of the blast in a high school. A 17-year-old student put this video on YouTube, showing the reaction in his physics class. Students screamed and ran into the hallways. He said some in the class thought war had started. Some of the incredible images were caught on cameras placed inside Russian cars. Many drivers now record their journeys in case of crashes or run-ins with police.
So there were a lot of these that could be found. And so we have the ability to see these happen. It would kind of take you by surprise if you had something explode in the air. And that's because that's not something we normally do see, right? All right, let's go back up here. So meteors burn up nonticulant clouds. Gosh, I should be able to say that. I shouldn't be recording these this late at night. They're nighttime clouds. They really appear up in the mesosphere. Radio waves bounce off this during the day. There's something called AM radio. Most of you maybe know about FM radio, but AM radio was the one that was here first, and then we got AM. AM became FM. And AM radio is really not as dependable at night because it's dependent on the sun interacting with this layer to create kind of a shield for it to bounce up and down. So sometimes at night, without that interaction with the energy from the sun, it kind of dissipates that blanket. So they're not always so good about bouncing off the atmosphere and coming back down. We have, if you look here, here's your ocean. Here is your troposphere, right? It's where we live. And then we have our gases riding up. So you'll see that our aerosols, our gases, actually do pollute. And they go all the way up, and they can go all the way up into the stratosphere. And we need to be careful with some of that because our pollution from one area travels all over. It's kind of like when we had the huge earthquake off Japan that created a tsunami. And they had three nuclear power plants that were really damaged. They were warning people in Europe that when the jet stream was over them, and that included us because it goes Japan, the US, and then Europe, that we would be getting some of the radioactive debris kind of raining down on us. So it's really important that we know that we live in this one big gas bubble, but there is no air. Like, this is the US air, this is the Mexico air, this is the Atlantic air, this is, Korea's air, this is France's air. It's all one big swirling mass. We all get it. In fact, we can find chemicals produced by 3M in the Arctic ice. So it's really all over the world. We know we live in a very connected place.
It's Middle School Earth Science Department. Today we're going to focus our attention on the layers of the atmosphere.
Is not here that I'm going to play it. I just wanted you to see that this is here. So if my explanation isn't working well for you, there is another option here if you want to go see somebody else, that's fine. And that should actually have been down farther, but I rearranged and I forgot to do quite so much because I was trying to get this video in here. All right, now let's go to the thermosphere. Mysteries of the sun. This is called the ionosphere, the thermosphere, and the mesosphere. This one is also one that you can go and watch if you wish. I'm not going to take the whole time to do it, but this is NASA, which is usually pretty good.
Heliophysics is the study of the sun and its interactions with the Earth and the solar system. The Earth's atmosphere has 4 primary layers. The lowest is the troposphere, then the stratosphere, mesosphere, and thermosphere. These layers, particularly the upper 3 and the existence of ozone in the stratosphere, protect our planet by absorbing harmful ultraviolet radiation. NASA scientists use balloons to collect in situ measurements of the atmosphere. Sounding rockets are used to collect more detailed data in the mesosphere and the thermosphere, both of which are too high for balloons. Satellites are also used to gather measurements of the upper atmosphere. NASA's Aeronomy of Ice in the Mesosphere, AIM satellite, remotely senses unique night-shining clouds made of ice crystals at an altitude too high for water vapor clouds. These noctilucent clouds form over the summer poles and vary in brightness throughout the year.
Kind of looks like an eye, doesn't it? That's just kind of a little... I started again. A kind of teaser. If you want to watch it, I would actually suggest using the link, because Schoology isn't always good about... Usually it lets me go to 5 minutes, but it's only letting me go about 1.5 minutes now on that one, apparently. So use that link if you're curious about it. But it really goes into a little more detail about how the sun interacts with those upper layers. But it gets hot, and I mean really hot, like 2,000 degrees Celsius hot. Oxygen and nitrogen absorbs the sun's radiation, and that's a big deal. Some of it gets through, some of it gets deflected and absorbed by gases and dust. Some of it's scattered, gets hit something and gets bounced back upward, and some of it hits clouds and gets reflected. So all of those things in the different layers can actually prevent some of the things from getting there. The ozone is a really good example of what can absorb and reflect and scatter incoming sunlight. But think of the fact that without that, we would have a lot of radiation coming at us. Cancers would be much more common, because we have something called an ozone hole at the South Pole. And of course, if you go to the southernmost tip of South America, that ozone hole will actually shift over it. And we now have things like SPF 50 clothing to help protect people, because they really had to do that. If the ozone, we have tornado warnings, right? Well, they'll have ozone hole warnings shifting, where they have to be really careful when they go outside, because a lot of the UV is not being absorbed and reflected back out. This is also where the northern lights occur. And if you don't know what the northern lights are, and I'm not going to play the music for that, but hopefully it will play. That's a bigger question. This was between the 27th and 28th of February in 2014, and this is northern Scotland. So they're a little farther north than we are, and so we can see northern lights here. Usually all the way down here they're going to be whiter, but the farther north you go, you see more of the colors, and that's the gases interacting like with oxygen and nitrogen, and each gas, when it's excited, creates its own color hue. And we have something called the color spectrum, a spectrometer, which allows us to see what gases are in different suns by what color of light color spectrum is emitted. And you can see greens and yellows and reds and a little bit of orange. All of them are different gases, fuchsias. Northern lights, if you ever get a chance to see them, and you can go farther north, they happen all year round. It just so happens that in the winter they're a little easier to see, because you don't have things like leaves on trees to block your view. In this case, they had a really good view because they were looking on one side of a lake, and you can actually see people stopping and taking pictures too. But northern lights are beautiful, but it is an interaction of the sun's energy with our upper atmosphere. Kind of looks like somebody produced it, right? But nope, that is our atmosphere interacting with the sun. That is all those energetic energy particles hitting gases in our atmosphere and making them, well, shoot an electron around to glow, give off energy. You can watch more of that if you wish. This is the layers of our atmosphere. If you want to go back and look at this, you are welcome to. I'm not going to do the whole thing. This is a droplet of water going through. It's a good one, but it's not worth my taking the time. But it's a good thing for you to watch, to review kind of like how water circulates through our atmosphere. We'll spend a lot more time talking about it too. So what changes the atmosphere? Pollution, ozone depletion, increasing greenhouse gases like carbon dioxide and methane. Cows are a huge producer of methane, by the way. That's what they fart out. Next thing you're going to need to know for the test is the atmosphere is composed of 78% of our atmosphere, that which we breathe in, is nitrogen, 21% oxygen, 0.94% argon, and then 0.03 carbon dioxide. And then you've got water, vapor, and a bunch of other like trace amounts of other things. That 21% oxygen is a big deal. If you get much more than that, like if you were around before the dinosaurs, there were times in our paleo atmosphere, in other words, a long, long time ago, where oxygen levels were actually much, much bigger, like right after the Carboniferous period, where they're basically, think of the planet surrounded with a big forest. It produced so much oxygen that if lightning struck, it could actually catch that area on fire. So it's a good thing, because right now if we have lightning strike, it doesn't make everything around us catch fire. So there are two ways oxygen can be released in the atmosphere. Water vapor breaking down, so H2O, releasing hydrogen and oxygen, or plants liberating oxygen from carbon dioxide. So what we exhale is carbon dioxide. What plants exhale is oxygen, which is a great, benefit to the two of us. Earth's ancient atmosphere, the original atmospheres, we'll talk a little more about paleo atmosphere, but it was really composed of methane and ammonia. What changed that deadly atmosphere? Well, sunlight triggered a lot of chemical reactions in the ammonia and the methane in the water. New gases formed, such as nitrogen, hydrogen, and carbon dioxide. That methane and ammonia almost vanished. What remained behind was the water, and water vapor broke down, hydrogen escaped, and left oxygen in the atmosphere. So we actually, before plants, did have some oxygen here already. Practically everyone agrees that the outer space begins where Earth's atmospheres end, but how you define where it ends is a big deal. So unfortunately, figuring out where the Earth's atmosphere ends isn't the easiest thing. So after all, there's no sign saying in the skyway from Cape Canaveral that reads, "Now leaving the Earth's atmosphere." So to be an astronaut in NASA says those who fly higher than 50 miles or 80 kilometers are considered an astronaut. But according to the European Aeronautic Institute International, a European body that regulates their astronauts, they say space starts at 62 miles up or 100 kilometers above the surface. So 50 miles, 100 kilometers, everyone's just using round numbers at this point. I'm pretty much going to say if you've been out where you were orbiting so fast that you were in free fall around the Earth, which is what the moon is doing, and which is what the space shuttle is going just fast enough to not crash, but not so fast that it skips out. I think if you're in free fall where you are experiencing weightlessness, I think I'm going to call you an astronaut. All right, so this is the first little precursor intro to our atmosphere. And as always, questions, follow up, we'll talk about it, and have a good day.